Today we're going to do Chapter 11, Lesson 2, which is exponential functions. So we've talked about these quite a bit this year, but today we're going to officially talk about what they are, what their formulas are, how they're defined, and then look at some real-world applications. So the first thing to look at is the definition here. An exponential function is a function in which the independent variable, which is the x variable, appears as an exponent. So if we look at the basic formula for an exponential function, it is right here. F of x is equal to a times b to the x power. And there's a couple of stipulations here. Number one, a cannot be 0. If a were 0, that would make the entire function 0 always. B cannot be 1. Let's think a minute, why can't b be 1? Well, you're raising b to a power, and 1 to any power is always going to be 1. So that would not be an exponential function, that would actually be a constant function or a linear function. And finally, b has to be greater than 0. We need b to be greater than 0 because we're raising it to a power, and depending on what the power would be, if b was a negative number, then if you're raising it to an odd number power, it would be a negative number, and if you're raising it to an even number power, it would bounce to a positive number, so it would bounce back and forth across the x-axis, and that would not be a good modeling function for us. The other hallmarks of this type of function is they do not have constant first or second differences. Instead, they have a constant ratio, and I'll show you what that means in a second. So if we look down at example 1, I actually filled example 1 out for you, but I'm going to help you see where this comes from. So f of x is equal to 2 times 3 to the x power. Well, if x is 0, this would be 2 times 3 to the 0 power. Well, anything to the 0 power is 1, so this would be 2 times 1, and that's why it's equal to 2. Similarly, if the exponent becomes a 1, it would be 3 to the first power. So this would be 2 times 3, and that's why that is 6. And you can see here pretty quickly the pattern that emerges. I'll just fill out the rest of this. And so on. So again, we talked about this idea of a ratio. We are multiplying by 3, multiplying by 3, multiplying by 3, and multiplying by 3 to get from one to the next. Now, interestingly, this concept of an exponential function actually works not just as growth. The number doesn't always just have to get bigger. We can also have exponential decay. And example 2 is an example of exponential decay. So this would be something, these are large numbers, so again, you see in this problem, it's population. This is a population model function, which is used in the real world. In this case, the function is 200,000 times 0.98 to the x power, and in this case, it's to the first power. So at year 0, this is just 200,000. As we keep going, we now have 196,000. And then to save some time, instead of writing this whole thing out, I'm going to just keep hitting the equal sign on my calculator. So that we can move on. But you can see that this is not a growth function, but a decay function because it is getting smaller. Okay, so why does that happen? Well, it has something to do with where we're starting. So you'll notice that the first number, the a term, is always our term 0. That was true in example 1. It's also true in example 2. But then what we have to look at here is what is happening with the number that is being raised to the x power. In this case, the number 3 made it an exponential decay. In this case, the number 0.98 made it. Oh, I'm sorry. In example 1, the number 3 made it an exponential growth. In example 2, the number 0.98 made it an exponential decay. So you have to ask yourself, what's the difference between the number 3 and the number 0.98? I'm sure you can figure that out, but we'll talk about that in a second. Let's move on to example 3, determining if a data set is representative of exponential growth or not. So as we look at the x terms, we see that we're adding 1 each time. Let's look at the y terms. What happens to the y terms as we do that? Well, clearly we're not adding something each time because that would be a geometric sequence. We're looking at an exponential, so we're looking for a ratio. So in this case, we're multiplying by 3. 12 times 3 is 36, and 36 times 3 is 108. So is this an exponential model? Yes, it is. Looking at part B, again, we are increasing by 1 in our x term each time. But what's happening to our y term? Is there a constant ratio? Well, in fact, no. There's not a constant ratio. There is a constant difference. So this is just an arithmetic sequence. So this is not exponential. And this is exponential. So let's formally look at the equation or formula. Again, for an exponential function. A couple things to look at here. Number one, on the left two, I'll circle them, the left two graphs here are representative of exponential growth. Now, what's the difference in the exponential growths? Well, it's really all about where the graph starts and what your exponent is. So we have, in this case, two examples, and I don't want to give too much away here, but the starting point is A, okay? Now, obviously, these two look very different. One is growing in the upward direction, and one is growing in the downward direction. And we'll see what factors are in play with that. But Basically, think about it like this. Exponential growth is going to be growth that is going away from the starting point, or growth that's going away from zero, whether it's in a positive direction or a negative direction. Exponential decay, on the other hand, think of decay as losing an absolute value. So it's going back to nothing. It's going back to zero. So we see this phenomenon in radioactive decay. We see it if we would set out a hot cup of tea or coffee. It would go back to room temperature or go back to zero if it could. Returning to homeostasis is a good way to think about this. So what you're going to do in the next few problems is do an exploration where you're going to be looking at what happens to my exponential function if a is greater than 0, if a is less than 0. And see how that has an effect on your graphs. So you'll be graphing these functions and making observations as to what the graph's going to look like based on your starting value, your growth factor or your decay factor. So let's formally, real quick before we end, let's formally talk about A. A is my starting value. And B, we'll call this a growth factor. If B is greater than 1, we'll call it a decay factor. If B is less than 1. And that should be enough information for you to make all your observations for the next examples. That's today's lesson on exponential growth and exponential decay. Thank you.